Here is the ball rotating on the table. So it says example 1. Apparently I went out of order and I apologize for that. So here is, you have a picture kind of like this, where I'm looking straight down at this thing, and here's the ball, and there's some mystical cord that's somehow attached to something else that's making the ball spin in the circle. So the force of tension is acting that way. And I'm looking straight down at this. This is a flat surface that I'm looking at, and this radius, do we have it? Yes, so this radius is 1 meter. And I know the mass of the ball, well, this is 0.35 kilograms. It's a frictionless surface, but it's kind of fun to remind ourselves that going straight down towards the center of the earth is the force of gravity, and coming straight up here would be the force normal. And then this would be my force tension. So if I'm looking down on this, and this is a solid table, I can't see the gravity vector going down below the table. And the normal is coming up out of the top of the table, and this is pointing towards the center of the table. So what the question wants to know is, what is the max velocity if the cord that's spinning this thing can only handle 80 newtons before it'll break? So this is where we first want to start. This is our center seeking force. These guys aren't doing a whole heck of a lot considering there is no friction. But I can still write out my sums. So like this, that my sum in the y, let's see, if I define, I'm going to do this, up and in. That's positive. Why? Because here is the direction of my acceleration. It always points towards the center of the circle. So to keep my life simplified with my sum of forces, I'm going to have acceleration and this force that are making that turn happen. I'll call those things positive. It just makes life easier. So then I have force normal is up minus the force gravity. It's not flying into the sky. It's not plummeting down to the earth. So this sum is 0. The sum in my x, well, that's also going to be the same as the sum for my center seeking. That is the thing that's making it turn in the circle. For this case, it is not an always. Don't let it be an always. So that is going to be, let's see, force of tension. And do I have anything else? There's no friction. There's nothing like that. So that's it. So force of tension equals the mass of the clay or the ball or the whatever that's going in the circle, v squared over r. Let's see. So I've been given tension, I've been given the mass of the ball. R is 1 meter. And velocity, oh, that's the thing we want. What is the max v? So let's rearrange that. So then force of tension times the radius. Just moving this up here. Divide by the mass equals v squared. Then take the square root of everything. So the square root of the force of tension times the radius divided by mass gives me the max velocity. Anything faster than this, and this line snaps. So that answers the question that we need. So let's just go ahead and put the numbers in there. So the force of tension, well, that's the 80 newtons. And this is 1 meter. It's nice for doing the math. The mass is 0.35 kilograms. And that will give me marker all over my hands. Let's see. So 80 divided by 0.35 to the square root gives me 15.11 meters per second. Should we verify that those units work? Let's see. A Newton, remember that's just F equals MA is how I can get there. F net equals MA. So MA, not G. So this is kilograms times meters per second squared. And I'm dividing by kilograms and multiplying by meters. Kilograms cancel, I end up with meters squared per second squared. Take the square root of that, that gives me meters per second. So I have the correct units, and that's it.